So today I'm going to be going through and I'm going to show how I use technology to work through a rational function, or why rational functions are in the form they are and how they work. Yeah. So I like to set up my tech stuff, or at least my technology layout, where I have my directions on the left and I have my hang on one second, I'm just going to up my audio a little bit so I'm not so dampened. There we go. Hopefully that's a bit better. My stuff's on the left and the other stuff's on the right. So as you can see here, I have it so that way that I can work in GeoGebra and I have all my directions right here. So we're doing choice 2. Let's get started. So I'm going to first take this parent function and have it on here, so that way I have my original parent function. That way I have, what it looks like. I'm going to change its color. Let's see here, settings. I'm going to change the color to gray. That way I know what it is. And style, let's make it dotted. There we go. So there's my parent function. Close that. All right, so I'm trying to figure out that for any function of the form of this, where these two are things in parent function. So yeah, so let's take a look. So the first question asks, use a graph tool to dynamically explore the rational function family. Consider polynomials up to 3 degrees of 3 for both p and q. Explain which parameters determine vertical asymptotes and why it makes sense. So what we're going to do, and vertical asymptotes, an asymptote, of course, is a line that runs vertically or horizontally that the graph cannot cross. It can get extremely close, but it can't cross it. And we can see that here. We have one horizontal and one vertical. So now I'm going to take another function. Let's take a different function, my bad. Let's define this as g of x. G of x equals, and I'm going to create p of x, q of x on the bottom, and p of x on the top. Whoops, let's make these lowercase. Might help a bit. Oh, for the love of goodness gracious. It's being a little difficult. But basically, I'm going to, instead do this. I'll create two functions. P of x equals, let's say, x cubed minus, or let's say p of x just equals 1 for now. And we're going to create another function where p of x equals, let's say, q of x equals x cubed plus x quantity squared plus 1. That'll work. So we have these two functions here. Now I'm going to turn these off. I don't want to see them. I just need the function. So now I'm going to write another function, g of x equals, and I'm going to have my p of x. I'm going to write it as a rational function, q of x. There. And here we go. So now we have, for my parent graph, a new graph, a very wonkin' looking graph. And let's use this. I'm going to use this to figure out the first couple of questions here. So it says here that consider the polynomial degrees up to 3 for both p and q. Explain why the parameters determine vertical asymptotes and why it makes sense. Okay, well, we're taking a look at vertical. So here's the thing. We see a vertical line here. This line is on 1, but it's not exactly 1. It's extremely close. I'm going to create another one. So I'm going to do r of x equals something. I'll do s equals something. Let's do r equals, let's try a function, another function on the top, or a bigger number. Let's do 4 for r of x, and again, I'm going to turn that off. And let's do for s of x, let's do square root function. Yeah, that sounds good. Let's do the square root of, I don't know, 2x minus 4. Let's get crazy. So now we're going to take that, and I'm going to create another function, g. Let's do h of x equals, and I'm going to put r. I'm going to take my r, put it on top, and I'm going to take my s and put it on the bottom. And I'm going to enter. I'm going to zoom out just a bit. And this makes sense that there's only one side because it's square root. And there's only one side, but you can see, again, that there's going to be some asymptotes here that are preventing it from crossing a line eventually. It's going to get extremely close to 1, but it will never cross 1. It's going to get close. And this holds true to anything in terms of the horizontal or the vertical. It'll get close to whatever it is. So yeah, let's take a look at these questions real quick here. So yeah, so using the graph, explain why which parameters determine vertical asymptote and why it makes sense. So the vertical asymptote, we're worried about the vertical. Well, we just saw this graph that the vertical asymptote was somewhere between 0 and -2. And we saw here that the vertical asymptote here is somewhere, it's actually 2. And if we look at that function over here, we can see that, judging by the looks of things, that the determining factor of that vertical asymptote more than likely is going to come from whatever the numerator is, from what I can tell. Whether that's correct or not is something that I could look further into, but I'm just going to be using this graph to determine whether or not, or I can define what it is. And to figure that out, let's take the same function from before. I'm going to change this guy from 4 to 3 and see what happens. It looks like it didn't shift. Let's try 1. Let's do something drastic. It looks like it went down. So it looks like that that at least to answer question 2, the parameter that determines how a function changes in terms of its asymptotes, the horizontal one, is the numerator, not the denominator. So there's a big thing, which leads me to believe now, by process of elimination, that the denominator is what's going to determine my vertical asymptote. And yeah, so let's take a look at how to modify that vertical asymptote. So let's go back to this function over here. I'm going to modify this guy. So let's make this 1. Whoa, that shifted. So now it's just straight up. Now it's at 4. Okay, so let's make this just the square root of x instead. I'm curious to see what's going to happen. Apologize for my phone going off. Okay, now it's actually gone all the way to where it's the vertical axis at 0. So it's obvious then that the denominator is what affects the value of the denominator, or whatever the denominator is, affects where the asymptote will lie. So let's get this guy back to normal. So we had him at 2x minus 4. I'd like to get my function back. Thank you. All right, so we've answered 1, we've answered 2. Let's move on to 3. 3, explain which parameters determine y-intercepts and why it makes sense. Okay, so we can see here the only graph out of all of these is g of x, which is generating a y-intercept. This one isn't because it's a square root function. It's not ever going to cross the y-axis because its asymptote is out here. It's not going to get close enough to intercept. However, it looks like that the parameter of the y-intercept is determined first by the denominator, and second, if the function has a y-intercept, meaning that it has to be like x squared or x cubed or x4. And to test that, we're going to go back up here and let's change this exponent to 4. Yep, that makes sense. Of course, it makes it go down like that, but that makes sense because 4. Let's try 2, and let's get rid of x squared. Yep, holds true. There's still a y-intercept right there. Let's do, so yeah, let's get this back to normal. So I would surmise then that the numerator of the function, given the fact that the function produces a y-intercept, is the affecting cause on what makes that y-intercept exist, because of course it's a function that will cross the y-axis. And also that the asymptotes are in the right position to affect that, meaning that the vertical asymptote has to be on the left or the right of the y-axis, meaning that it has to be enough to where it will allow it to cross, and it's not the y-axis. If it is the y-axis, there won't be any y-intercept. So that right there is why that happens. So that's the answer number 3. Let's move to number 4. So number 4 says, explain which parameter determines whether or not the function is increasing or decreasing and why it makes sense. Okay, so this one is a little tricky. When I look at this graph, the first thing that pops in my mind when I say this is it depends on which direction we're going. That being said, judging by the fact of how it moves left to right, if we're looking at this from the fact that we're going from left to right, then it's going to be decreasing. That's going to come up here and it's going to decrease again. So it'd be decreasing from left to right. If we're going from right to left, and I'm referring, of course, to g of x, let me turn off h to avoid any confusion, then we can see that the function will be increasing from right to left, meaning that I'm going to come here, I increase, so I'll zoom back down here, and I'm still increasing. So technically, the graphs can increase and decrease either way. It depends on which direction you're going. It does not depend on the function itself. It depends upon whether or not you're traveling from left to right or right to left. So those are the 4 questions I've answered. And just to quickly sum up here in the last about 50 seconds I have, I'm going to quickly go over the fact that this function, how I determined all these questions, is simply by just going through graphing these. I'm not looking, from what I could see, I'm not looking for any numerical or arithmetic-based answers. I'm not using any kind of basic balancing or substitution to try and determine this. I'm simply observing a graphed function. So I think I'm going to end it there. But that's how I would use technology to figure out rational functions using GeoGebra, and how I would determine and answer these 4 questions. Thank you much for watching.